Meteors have the power to transform our planet, to wipe out huge swaths of life on Earth in one impact. But not all are that dramatic. We are hit by more than 100 tons of small, sand-sized particles every day, and they are essentially unnoticeable. About once a year, a car-sized meteor comes crashing through our atmosphere, but the resultant, impressive, fiery streak burns up long before hitting the ground. It's only on the scale of millions of years that we are in danger of being hit by meteors a kilometer or two wide, big enough to do some serious damage. But we've not seen one of those since the dinosaurs. Lucky for us. But size isn't everything. In fact, the biggest impacts may not even be from the largest objects. If one particularly interesting theory is true, some very rare meteors may be made of something a little more exotic than rock. Externally, there would be not much to differentiate these rarer meteors. In the vacuum of space, they would appear exactly the same as any other space rock. But while regular meteors might create a fiery streak in the sky, these outliers would have impacts that exceed the largest of nuclear bombs. And those are just the small ones. If a kilometer-sized meteor of this variety hit the Earth, similar in size to the normal meteor that killed the dinosaurs, we might not have a planet anymore. That is the power of a meteor made of antimatter. Could antimatter meteors really exist? What clues would help us identify them from regular matter meteors? And how big would they have to be to become a major problem? I'm Alex McColgan, and you're watching Astrum. Join me today as we test the scientific theory behind antimatter meteors and explore the odds of such objects lurking in our solar system.
Antimatter is a funny substance. The fact that it exists means that we shouldn't be here.
It is almost identical to regular matter, with a few key differences. One is that it has an inverted charge. Another is that when antimatter meets regular matter, the two annihilate each other completely, converting almost entirely into energy.
Now, in the early universe, it wasn't just matter that was created. In theory, an equal amount of antimatter came into being too.
All the matter should have bumped into the antimatter, and everything would have cancelled each other out. This would have left no universe for us, as there would be nothing to make the universe out of. It is one of the mysteries of science that this did not happen, and for some reason a slightly larger amount of matter coalesced into existence than antimatter, perhaps as small a discrepancy as 1,000,001,000 matter particles to every billion antimatter ones. Scientists are still trying to figure out why this might have occurred, but the mystery remains unsolved for now. Perhaps there is some rule at play that we've not yet identified. Whatever caused it, this imbalance is the reason the universe we see around us is almost entirely made of regular matter, and the only place we reliably see antimatter is when they make tiny amounts of it in experiments at CERN and in other particle accelerators. Some hospitals even have small particle accelerators to create positrons for PET, or positron emission tomography scans. However, just because we don't see it doesn't mean that tiny pockets of antimatter couldn't exist. When the raw, primordial soup, quark, gluon plasma of the Big Bang began to form into particles, while overall there would have been more matter than antimatter, in local areas there were fluctuations. So it's logical that clumps of antimatter could have emerged and dominated as gravity pulled them together. After all, if you flip a coin enough times, you'll inevitably end up with runs where you flip nothing but heads or nothing but tails. If these clumps were large enough in scale, they wouldn't annihilate away in a burgeoning solar system. Instead, they would be the solar system, and it would be pockets of matter that would eventually annihilate out, leaving behind stars and protoplanetary disks made entirely of antimatter. This seems highly theoretical, But could such solar systems actually exist? I personally think it would be really cool if they do, and should we ever find one, it will certainly be breaking news. If you want to be the first to know when a story like this does break, and keep up to date with other slightly more likely discoveries too, then the best place to find them is the Astrum newsletter. This is a weekly update sent straight to your inbox, specially curated by the Astrum team, and packed with not only the latest spectacular space stories, but images, links to some of my all-time favorite Astrum videos, and the chance to get in touch with us directly. Ask us a space question, and we'll do our best to answer them. For now though, let's get back to the antimatter at hand. For the most part, an antistar would be visually identical to a regular one, as antimatter behaves in all the ways you might expect matter to. It obeys the same laws of gravity, and mostly looks the same. The only telltale giveaway would be when regular matter interacted with it, such as when the interstellar winds met the edge of the fledgling solar system, and resulting annihilations would emit gamma radiation. And curiously, there are some systems that seem to do this. 14 such gamma-ray emitting star candidates were found in the Milky Way thanks to the Fermi Large Area Telescope in 2021. If these are antistars, and their profiles do match what we would expect out of antistars, so this is not ruled out, and they're not other objects that emit gamma rays like pulsars or black holes, then systems made of antimatter with planets and asteroids do exist. The ratio of antistars to stars would be about 1 in 400,000. So the stage is set. If antistar systems could exist, it's not illogical to think that antimatter meteors do too. And that leads us to the question, what are the chances of them coming to Earth? The idea of antimatter meteors striking our planet is not a new one. Even back in 1940, only a decade or so after the discovery of antimatter as a concept, Russian-American physicist Vladimir Rozhansky began to speculate about their existence. All it would take was for our solar system to have passed one of these antimatter solar systems at some point in the past. The sun's gravity would then knock a few outlying antimatter meteors out of their precarious orbits and into ours. Antimatter meteors may not have been able to form in our solar system. Their particles would have been annihilated by interaction with matter far too early for that. But in space, just an empty vacuum, somewhat devoid of matter, there would be nothing for them to annihilate with. So there's a chance they could be among us. And if they were, would we even notice? Soon after Rozhansky, American astronomer Lincoln LaPaz began to wonder whether any of the craters on Earth could be attributed to antimatter meteors. So perhaps this is the time to consider what an antimatter meteor could do if it came in contact with the Earth, so we know what to look out for. Thankfully, it's not necessarily a simple journey. The first issue such an antimatter meteor would encounter before reaching Earth would be our atmosphere. To be fair, this is a problem for regular meteors too. When one of those trades vacuum for air, the speed at which it's traveling causes it to generate incredible friction, causing some or all of the meteor to burn up on the way down, depending on its starting size, leading to the fiery streak I mentioned at the start. However, antimatter meteors would have it much worse. Each particle of atmosphere that the antimatter meteor encountered on the way down would annihilate a similar amount of the meteor. So to understand what happens next, we need to turn to Einstein's famous equation, E equals mc squared. The meteor's mass, multiplied by the speed of light squared, tells us how much energy would be released by the meteor on the way down. Technically, twice that, as for each particle of the meteor that's annihilating, a particle of atmosphere is doing so too. This is potentially a huge amount of energy being released. Let's do a bit of a thought experiment to work out how much. While the dividing line between the atmosphere and space is either 100 kilometers up if you're talking to Europeans, or 80 kilometers up if you're talking to Americans, as the two haven't reached a consensus on that point yet, Over 90% of the mass of Earth's atmosphere is actually clumped below 16 kilometers, clinging to the planet as closely as possible thanks to the pull of gravity. So by working out how much air exists between this line and the Earth's surface, we can get a rough idea of how much antimatter you'd need to have before an antimatter meteor hits the ground. This is a little tricky to calculate, but thanks to a chart released by the International Standardization Organization, I was able to add up the sum total of the atmosphere at different elevations between the surface and 20 kilometers high, and found that in a 1 meter by 1 meter corridor between space and the surface, you'd have roughly 10,132 kilograms worth of atmosphere. A meteor would need to be roughly this large to even hit the surface, assuming it traveled the most direct route straight down. Now, antimatter is similar in mass to matter, so we can assume that they would have comparable compositions too. Most meteors are made of chondrites, so assuming an average antimatter meteor made of the antimatter version of the same stuff, we can put the density of our antimatter meteor at around 3,400 kilograms per cubic meter. Of course, there's then a balancing act you need to do. The bigger the meteor, the larger the surface area, and the more air it thus encounters before it reaches the surface. However, as volume scales up in cubes, while surface area is only squared, there is a sweet spot you can hit where the amount of air being annihilated by the meteor would theoretically perfectly match the amount of mass the meteor possesses. And then we know that any mass of meteor above that would make it through the atmosphere to hit the ground. Using very rough maths, I found that a 3 by 3 by 3 meter meteor, or 27 cubic meters, worked best for this calculation, which had a mass of 91,800 kilograms, or 3,400 kilograms per cubic meter times 27 cubic meters. This would only encounter 91,191 kilograms worth of air on the way down, meaning 608 kilograms worth of meteor would actually hit the surface. That's approximately the mass of a large grand piano. How much damage could 600 kilograms of antimatter actually do? It's time for our equation, E equals mc squared. Using this calculation, we learn that 600 kilograms of remaining meteor releases 5.4 times 10 to the power 19 joules of energy, or 54 quintillion joules. Then double that, as the ground being annihilated releases that amount too, so 108 quintillion joules. For a point of reference, a 1 megaton nuke gives off 4.18 times 10 to the power 15 joules of energy. Even if we scaled up to the largest nuke ever detonated, the Tsar bomber, which had a yield of 50 megatons, we're still only looking at 2.09 times 10 to the power 17 joules, a full 5,000 times weaker than our antimatter grand piano. And the Tsar's bomber blast was so great, towns within 55 kilometers, like Seveny, were leveled. Wooden buildings 160 kilometers away were reportedly damaged. The light from the blast was seen 1,000 kilometers away. Windows in Norway and Finland were shattered by the explosion. If just 600 kilograms of our antimatter meteor impacted in the middle of a state like Texas, the whole state would be destroyed. The center vaporized, the rest devastated. This is just the energy release from our antimatter meteor annihilating on the ground, not even going into things like kinetic energy. But even then, it's actually not just the 600 kilograms that hits the ground we need to worry about. When you consider the rest of that 91,200 kilograms of mass that was annihilated in the atmosphere, the blast radius becomes a lot bigger. While some of that energy would travel upwards into space, minimizing the damage below, suddenly you're not just worrying about Texas. You're worrying about the entirety of the USA. All that's just from an antimatter meteor that's comparable in size to a car. We really do not want to get hit by an antimatter meteor. So what actually are the risks here? Let's say that an antimatter meteor had got swept up in the sun's gravity well millions to billions of years ago. Could it now be one of the 40,155 near-Earth asteroids that NASA tracks? The good news is no. For one simple reason. Space isn't actually empty. While we talk of space being a vacuum, even in space, there are trace amounts of dust floating in the void. As such, an antimatter asteroid traveling even through the interstellar medium would not likely have a survival rate of longer than around 300 years. As we last clipped another star 70,000 years ago, Schultz's star, in case you're interested, it would have to have been an exceptionally lucky antimatter meteor to not only dodge all the other asteroids in that time, but also to have not encountered enough dust since then that it would have disintegrated into gamma radiation. For this same reason, an interstellar antimatter comet coming through our solar system would be unlikely. Small ones would burn up before reaching us, and larger masses would be noticeable. They would emit a steady stream of gamma rays as they traveled, making them detectable to our telescopes. No such sparkling asteroids have ever been detected. So, all in all, while it would be devastating to be hit by an antimatter meteor, it is unlikely that one would survive long enough to reach our planet, assuming they and antimatter stars exist in the first place. We are probably quite safe. Besides, if antimatter meteors existed, we might have seen some evidence of them before. Meteor impacts with unusual destructive capacity, but leaving no traces of the meteor that caused it. We've not seen anything like that. Have we? In June 1908, a fireball lit up the sky in a remote part of Siberia. The meteor exploded before hitting the ground, its detonation causing massive forest fires and sending trees crashing to the ground like bowling pins in an area of destruction kilometers wide. Witnesses more than 30 kilometers away reported seeing a flash brighter than the sun, followed by a roar of thunder. Due to its remoteness, scientific teams did not arrive at the site until 1927, but even then, the destruction caused by the blast was easy to see. Strangely, for an object that caused such destruction, almost no trace of the meteor was ever found, beyond a few microparticles. But the Tunguska event couldn't have been caused by an antimatter meteor, could it? Don't worry, we know that it probably wasn't an antimatter meteor, but there was a lot of debate about the topic in the past, and we couldn't resist being a little spooky. I'm happy to announce we have a weekly newsletter to keep up with all the discoveries in our cosmos, and our designer Peter has made the most beautiful email you'll ever receive. Sign up with the link down below. It's the best way to stay connected between videos. Short, focused updates on what's new and fascinating in space each week. No spam, no filler, just the good stuff. You'll get the latest news, visuals, and insights delivered straight into your inbox. If you enjoy Astrum videos, you'll love this. Join the newsletter and stay curious with us.